Hello and welcome to this brief video on escape speed. What is escape speed, you may ask? Escape speed is the speed required for a projectile to leave the Earth's gravitational attraction. So it's the speed required to get out of it. And it's really important for, let's say, launching rockets is a good example. And crucially, it's to get to infinity. Infinity being the place where there's no longer any potential energy. Okay, so this is what we're going to be thinking about today. Let's go on with that. So if the potential of the Earth's surface is measured by a minus gravitational field constant multiplied by the mass of the Earth divided by the radius of the Earth, that gives us the potential on the surface. Then the potential change to get to infinity is related by the potential multiplied by the mass of the object. Okay. So that gives us some idea about the potential change required to be able to escape. So it's a good starting point. So we know how much potential energy is required. From this, we know that the kinetic energy has to be at least equal to this. So therefore, half mv squared equals that potential energy. If we rearrange this for v, we can see that the square root of 2 times the gravitational constant multiplied by the mass of the Earth multiplied by the radius divided by the radius of Earth gives us a value for v, and we know that little g is equal to g times mass of the Earth divided by radius of the Earth squared. So we can substitute that in. That gives us a really simple equation for calculating the velocity required to escape planet Earth. So therefore, the escape velocity, this means the resultant total gravitational potential energy and kinetic energy at a large infinite distance must be at least 0. Okay, so the two things cancel out. So look at this question. Find the velocity of a tennis ball must be thrown vertically upward to escape from the Earth. Recognizing g equals 6.67 times 10 to the minus 11. The mass of the Earth is 6 times 10 to the 24, and the radius is 6.4 times 10 to the 26. 10 to the 6, I mean. Okay, take a moment, make that calculation. Should come up with 11 kilometers per second. That is a pretty fast tennis ball that you would have to throw. Obviously, on planet Earth, we have some values, but depending on the mass of the planet, we have different escape velocities depending where you need to be. So it's only 4.3 kilometers per second for Mercury and a whopping 60 kilometers per second to throw a tennis ball off Jupiter. There's some implications here. So remember that complete escape is not really possible. Gravitational attraction is infinite. So the gravitational force will always be there no matter what. And this explains why some planets have atmospheres and others do not because of this value. Lighter molecules have higher average speeds and are more likely to reach escape speeds. So therefore, the atmosphere to deplete. I should mention about black holes as well. Black holes are related to the escape velocity in quite an advanced manner. So a black hole is the remains of a star that's collapsed under its own gravity. We know that. Now, the escape speed for a black hole is really large due to the fact it's really, really, really massive and has a very, very small radius. Now, if the escape speed exceeds the speed of light, that means radiation cannot escape, and therefore it appears black. And there's a critical radius at which the escape speed equals c, and this is known as the Schwarzschild radius. And that defines where we have something called the event horizon. This is an imaginary surface in which no light can escape. And this is the limit how close you can approach the black hole as well and still be able to escape. Although it has to be said you wouldn't want to get that close anyway because you'd be stretched like a big elastic band and it'd be very, very painful. I wouldn't want to wish that on anyone. And that gives us an overview of escape velocity all the way from planet Earth to a black hole.